In 1952, the UK was the first in the world to use the first jet airliner, the de Havilland Comet. The aircraft cruised at a speed of over 700 kilometers and an altitude of 13,000 meters. It was fast and stable, making the British proud. But just 2 years into operation, the aircraft experienced 3 major accidents, all involving in-flight disintegration. British Prime Minister Churchill ordered a thorough investigation into the air accidents at all costs. Investigators then built a large water tank, placed the aircraft inside, and repeatedly filled and emptied the tank to simulate the pressure changes experienced during takeoff and landing. In less than a month, the skin of the aircraft began to crack, extending from a corner of the aircraft window. The investigation results released in 1955 pointed to the culprit of the air accidents, the aircraft's square windows. From then on, structural engineers met their lifelong nemesis, stress concentration. Stress concentration refers to the phenomenon where the actual stress in a structure exceeds the nominal stress. The severity of stress concentration is usually measured by an index called the stress concentration factor, defined as the ratio of the maximum actual stress to the nominal stress. For example, consider this perforated plate under tension. According to this stress calculation formula, F divided by A, its tensile stress should be 120 MPa. But in reality, the maximum actual stress at the edge might reach 200 megapascals. So the stress concentration factor is 1.67. Stress concentration combined with metal fatigue is frightening and could likely lead to structural failure. For instance, the cracks extending from the square windows of the Comet aircraft. Stress concentration is quite common, such as defects in processing, material defects, and connections between different materials, all of which can cause stress concentration. The most frequent encounter is geometric discontinuity or sudden geometric changes in structures, including sudden corners, holes, and notches. Do you suddenly feel that all structures are so fragile? Every time I draw, I have the impulse to give up because I don't know where to start. Stress concentration can only be mitigated, not eliminated. After all, I-beams cannot be without corners. Plates cannot be without screw holes. Bearings cannot be without keyways, and the blogger cannot be without your likes and follows. As long as stress concentration is not excessive, the structural design is fine. As for what is considered not excessive, it's hard to say. Each industry has allowable stress for the corresponding materials. For ductile materials like structural steel and aluminum alloys, allowable stress is generally the yield limit divided by 1.5 to 2.5. For brittle materials like cast iron and high-strength steel, allowable stress is obtained by dividing the strength limit by 2 to 5. In the mechanical design industry, there's a book, a timeless classic, the Practical Stress Concentration Handbook. It uses curves to tell you the stress concentration factor corresponding to various structures. The handbook was published in 1984 and still shines brightly today. Isn't that why the mechanical industry is more valued the older it gets? But now it's 2025 and checking manual seems a bit clumsy. For example, if I asked you to check a table and tell me the stress at the root of the fan blade when rotating at 3,000 revolutions per minute, the experienced masters would shake their heads. Nowadays, the more mainstream method for analyzing structural strength is computer finite element analysis. For example, the famous structural simulation software AFEM calculates accurately and quickly and is also very easy to use. I believe that after using it, second-year undergraduate students would exclaim, "So this is what structural simulation is like." Now let's try a couple of examples. First, a simple one, an iron rod with a sudden change in diameter under tension simulated to have a maximum stress of 343.3 MPa. And look, the maximum stress is at the point of diameter change. Stress concentration is quite obvious, so how to handle it? It's simple, add a chamfer to the change in diameter to make the transition smoother. Simulating again, the maximum stress drops to 293.1 MPa. Although the maximum value is still at the point of diameter change, meaning stress concentration can be completely eliminated, its severity is clearly reduced. Then try the fan that makes the masters shake their heads, calculating the stress at the root of the blade when the fan rotates at 3,000 revolutions per minute. The model is imported into AIFEM, a rotational speed is given to the fan, and the simulation results in its maximum stress being 278.4 MPa. To be honest, this stress is already very dangerous, exceeding the yield stress of commonly used steel at 235 megapascals. What to do then? Well, you need to switch to higher strength steel or add a chamfer at the root of the blade to reduce stress. Of course, you can also reduce the rotational speed. As for the specific reduction amount that is suitable, I'm too lazy to do it, you can try it yourself. Download AIFEM from the Tianfu Software official website for a free trial.